Okay, thank you again, Gil. And we'll move to the next talk. The next talk is by a group from the Technion. The speaker is Igal Bayn, and the title is Single Crystal Diamond Photonic Crystals Nanocavity Fabrication.
Thank you, Mr. Chairman. Hello, everyone. So, my name is Igal Bayn, as far as I remember, and today I'll discuss the photonic crystal nanofabrication in the single crystal diamond, the most hardest material on Earth. I'm working in a group of Professor Zaltzman and Professor Rafi Kalish, and together with me on this project worked Dr. Boris Myler and Vladimir Richter. So, let's start. The first thing is to explain why is it interesting to deal with single crystal diamond photonic crystal. And there are actually three whys. The first one, why single crystal? The second one, why diamond at all? And why photonic crystal? I'll give a brief introduction on photonic crystals in general, and then I'll answer this question. Hopefully, the answer will be large-scale, room temperature quantum computation. Then I'll go through the diamond photonic crystal fabrication technology, describing you the challenges that are hindered in a single crystal diamond fabrication, the membrane formation, the photonic focused ion beam patterning, and photonic crystal nanocavity fabrication. At the end, I'll show you the first optical microphotoluminescence characterization of photonic crystal in diamond. So let's start. The first thing, hopefully it will be better, much better. So the first thing is why diamond? Actually, as all of you know, diamond is an extraordinary material, not only due to its mechanical and optical properties, but also quantum mechanically. If we take a diamond structure and substitute a single carbon atom with nitrogen and vacancy, we obtain a nitrogen vacancy color center, or envy center shortly. Its energy diagram is shown here. Its ground state is formed of a triplet, while its lower ms equal to 0 state is optically active and can be read out with a standard solid-state red laser, and its upper state, ms equal ±1, is optically inactive. All these properties allow us to measure a single spin in a room temperature, which is, in my opinion, or as far as I know, the only system where it is possible. Moreover, envy center has some other extraordinary properties, such as very long decoherence time, stark shift of the optical transition, this one, is enabled, no photo bleaching in envy center occurs, and Rabi oscillation and simple 2-qubit operations were demonstrated in the room temperature. All these properties make diamond very attractive for quantum information technology. Moreover, I'll try to persuade you that incorporating this envy center in a high-Q diamond photonic crystal nanocavity will allow the realization of a large-scale quantum computation. But the first thing, as far as I understand, there are many materials engineers here in the audience, so I've got to give some introduction on photonic crystals in general. For our talk, photonic crystal is the array of air holes which are patterned in the diamond membrane. These air holes provide or produce photonic bandgap, which is very similar to the solid-state one, and this bandgap is the region in the frequencies where light cannot propagate. The detailed wavelengths of this photonic bandgap are defined by the radius, the pitch, and the thickness of the membrane. Now, we would like to form a photonic crystal cavity, which is actually a light trap, where the light will be trapped as long as we can, and this cavity is formed by local dielectric constant modulation, which introduces the effective defect into the bandgap. The light then is localized by mainly two mechanisms, total internal reflection and photonic crystal confinement, which is actually the Bragg confinement. So, to form a high Q cavity, this is the cavity where the light decay is the slowest, we've got to limit our losses. Our lateral losses along this membrane can be ultimately limited by adding additional number of photonic crystal layers. While our vertical losses, which are defined by total internal reflection, they will define the quality factor of this nanocavity. Now, We are trying to localize light in a very small area. When we localize light in a small area, it is delocalized in a K-space, just uncertainty principle. So we've got a distribution in the K-space, which can be defined in two groups. The first of them are the confined modes, which experience the total internal reflection. And the second of them, positioned in the light cone, are the radiated modes, and they define our losses in the vertical direction. So the idea to form the high Q cavity is to take our distribution outside of the light cone. In the diamond, it is just like this, from here to here. In diamond, this might be more tricky because of its lower dielectric constant. So, in our group, we have derived the cavity design, which produce theoretically ultra-high Q nanocavity with the quality factor over million. This cavity, to fabricate, we've got to move the holes outside of the linear defect, which is actually photonic crystal waveguide. The whole shift precision must be around 5 nanometer, and also we must work with a very high quality material. So to start and to realize the first photonic crystal nanocavity, we decided to go to somewhat modest tasks, which are moderate quality factor cavity, and they are formed by 3 missing hole technologies. So we take this photonic crystal and just miss 3 holes in the middle. We obtain, or we should obtain, the quality factor of 800. Now, when the idea of design of photonic crystal is clear, I can turn to the fabrication. The fabrication is in a single crystal diamond, and this is the last why, because optical losses in single crystal diamond are much lower. So, just a second. Before I'll go through the fabrication diamond qubit. So, when we've got this photonic crystal cavity, and there is envy center inside, we would like to realize a large-scale quantum computing. Large-scale quantum computing for us is many qubits. Up until now, all realization of quantum computation in diamond were done when occasionally 2 envy centers were positioned one nearby the other. So their interaction, which was naturally dipole-dipole interaction, was limited totally by several tenths of nanometer. If we would like to go in the future to the large-scale quantum computing with many envy centers, we will have to have the envy center inside the cavity. Each envy center is localized to the cavity, and the interaction between distant envy centers, which might be positioned tenths micron away, is via emitted photons. So in this case, we've got to have the photonic crystal cavity. We've got to fabricate the photonic crystal waveguide and position the envy center inside. Throughout all this work, we use type 1b diamond, which is enriched with envy center, so we do not have a single envy center, but the whole area here is enriched with nitrogen. Now, let's go for the fabrication. Single crystal diamond photonic crystal realization requires new microfabrication technology, since first, no chemical diamond etchant exists. No photolithography process for diamond is developed. The membrane formation is very challenging. And we have proposed the solution where the membrane is formed by an under mega electron volt ion implantation and selective etching. The photonic crystal is patterned by focused ion beam. So let's start with the membrane. We've got this type 1b diamond sample. We irradiate it with helium implantation. This helium implantation forms a buried damage profile, and this profile under a subsequent thermal annealing is graphitized when the damage density is higher than a certain threshold. It can be etched out, and we obtain a freestanding membrane. Now, this graphical picture shall be somewhat more complicated, because for photonic crystal to operate in the visible range, we've got to have a sufficiently thick membrane with a large air gap underneath to localize the light sufficiently far from the substrate. So we have got here the following implantation strategy. There are 4 helium implantation. In the red is the sum damage for the membrane. When the damage density is higher than the threshold, it turns out to the graphitized layer under thermal annealing, and this layer can be etched out. Here you can see the border of the edge etchant reach up until this border. Here is the membrane, and here is the air gap. If you would continue the chemical age, it will go all the way left. Now, when we first have this single crystal diamond membrane, the first thing we would like to do is to characterize its defect. And the first thing we've done is the characterization of surface roughness. We have characterized both the upper and the lower side of the membrane. And here you can see the AFM, which is the square of 10 by 10 micron. You can see that the RMS of the upper and lower surfaces are identical, which means that our implantation process, which include ion implantation and amorphization, do not introduce additional defect, which is certainly good. This linear defect that you can see here are caused apparently by the polishing. Now, when we've got this membrane, we have to measure or characterize its thickness. So we cut the cross-section, and during the cross-section cut, there is a ready position of carbon on the lower edge, both here and here. As a result, when you look at this picture in the SEM and you toggle the brightness or the contrast, you can see the ambiguity in the thickness measurement, and this ambiguity can reach 100 nanometer, which is totally unacceptable for precise optical device. So to tackle this problem, we have milled and trenches in the diamond and deposited platina, which actually grounded both the upper and the lower edges. In this way, you can see a very uniform measurement of the thickness, which turned out to be 345 nanometer. Now, in order that cavity would operate in the visible region, which is the photoluminescence of NV defect, we've got to make it the thickness of 150 to 220 nanometer. So we milled up the well with focused ion beam, and into this well we have produced the photonic crystal cavity, which is 3 missing hole cavity. You can see here the masterpiece of astigmatism and focusing, because the radiuses here are very, very uniform on a nanometer level. And generally the hole here, the pitch is 250 nanometer, the radius is 88 nanometer, and the thickness is around 200 nanometer. All these geometry parameters are important since they define the wavelength and the quality factor. Certainly, inside, we would like to position single envy center, but since it is a yellow diamond, it is full with envy center, and this job was done for us before. So, now, we have produced an array of photonic crystal cavity with different designs, and this one is an ultra-high Q nanocavity with a photonic waveguide inside and hole shifted by several nanometers. Both of these were not characterized optically yet. Now, to the optical characterization. We have excited our cavity that I have shown you a few slides ago with a green light and measured the photoluminescence in the red light. The photoluminescence shows this magnificent peak in 612 nanometer. As far as we understand, this is the first time the single crystal nanocavity is measured and characterized. This peak appears only in the vicinity of the cavity and disappears outside. When we change the polarization, the peak also disappears. So let me say that this is the first time that this cavity was realized. The quality factor is 500, which is compared to our calculation or calculated value, which is 800, suggests that we are in a high quality material. Now, let me go for results in conclusion. First of all, we have shown here the single crystal diamond photonic crystal fabrication. We have shown the first optical characterization of photonic crystal nanocavity. As for the future work, we would like to focus on cavity wavelength control, the elaboration of material losses, and going from single envy centers and going from multi-envy centers to a single envy center implantation. So, summing up, we are focusing on producing the most expensive photonic crystal on Earth, but it's definitely worth it. And let me finish this presentation with photonic crystal in arts by the courtesy of Antonio Gaudi. Thank you.
Thank you, Igal, for this nice talk. We have time for short questions. Yes, please. Try to raise your voice.
Yes, well, the answer is this technique not. But you see, milling is working throughout all the samples, so I cannot modify it and make it three-dimensional. What I've got to do is to make these holes and to stack them together. And there are groups in Japan who did it. Currently, all the world is working on a planar or two-dimensional photonic crystals. The quality factors are very, very high. And the complexity of the stack procedure, which is possible, and we have done it in our group, is so high that it doesn't worth it.
Okay, any more questions? If not, thanks to the speaker again, and we'll go to the next speaker. So the